Hello, everybody. My name is Satoshi Hoshino. I am from Utsunomiya University, Japan. The title of my presentation is Multiple Cooperative Searches for Aerial Surveillance. Okay, first off, as you can see in this movie, we have so many aircrafts in our airspace. Many of the aircrafts are equipped with a so-called ADS-B for identification. However, 30% of all the aircrafts are not equipped with the ADS-B, or the ADS-B is broken. Because we cannot identify such aircrafts, these aircrafts have negative impacts on the air traffic. For this issue, we focus on aerial surveillance systems. In recent decades, unmanned aerial vehicles, UFV, have been employed for the surveillance application. So we focus on an aerial surveillance system composed of multiple UAVs. As you can see in this figure, the aerial surveillance system is composed of a sentinel and multiple searchers. The sentinel operates at a place higher than the searchers. A sensing range of the sentinel is drawn by this pink circle. If an identified event occurs in this surveillance area, the sentinel detects the position. However, the sentinel is not capable of identifying the event precisely. On the other hand, the searchers are able to identify the event in the sensing range drawn by these red circles. As the surveillance surrogates, undefined events such as wildfires have been assumed. Such static targets occurred randomly at any place. On the other hand, we assume unidentified flight vehicles, UFVs, as the surveillance targets. Compared to the static targets, searchers are required to approach UFVs in consideration of the movement. Within the surveillance area, the sentinel constantly tracks the positions of searchers and UFVs. The searchers are allowed to communicate with the sentinel. So a searcher has information about the target UFV and other searchers via the sentinel. This figure illustrates the top view of the surveillance system with 3 searchers for an UFV as the target. The pink circle indicates the surveillance area. The UFV moves below the searchers. Once the UFV is detected by the sentinel, this detection information is shared with 3 searchers, and the searchers begin to approach the UFV. Eventually, a searcher succeeds in detecting the UFV within the red sensing range as shown in this figure. On the other hand, the UFV reaches the destination without being detected by the searchers in this figure. In this case, the searchers fail in detecting the UFV. In this system, UFVs in the surveillance area are allowed to move toward the destinations while avoiding the searchers. In addition, the UFV is faster than the searchers. Therefore, as can be seen in this movie, it might be difficult for the searchers to approach and detect such sophisticated and interactive UFVs as long as the searchers approach independently from each other. For this challenge, cooperative approaching actions among the multiple searchers play an important role. Therefore, we apply reinforcement learning to the searchers in consideration of the interaction between the searchers and UFV. For reinforcement learning, the surveillance process from the detection of the incoming UFV by the sentinel to the success or failure of detection by the searchers is called episode. At the end of each episode, a reward is given to the searchers depending on the surveillance result, success or failure. With each episode, the searchers gradually learn effective actions to approach the UFBs. For cooperative surveillance, the searcher state is defined on the basis of the relative position and the direction to the target UFB and other searchers. For this purpose, the polar coordinate system centered on the host searcher is used for state definition. In this figure, the positions and the moving directions of the searcher and the UFB are represented by X, Y, and theta in the 2D plane. The information is known to both the searchers and UFB. Here, D and theta indicate the distance and the direction angle of the searcher to the UFB, respectively. Relative direction between the searcher and the UFB, which is phi s, is further included in the state. In the right figure, D and theta indicate the distance and the direction angle of the searcher to the other searcher. So ST, the searcher state at time t in an episode, is defined by the combination of D and theta in addition to ds, theta s, and phi s. Therefore, it is expected that the searchers can learn the approaching actions, taking the moving direction of the UFB and the cooperative relations with other searchers into account. In a state, searchers take actions so as to approach the UFB. The searcher action defined by the directional change and the moving distance is represented as you can see here. Given continuous values of the directional change and the moving distance, the action space becomes too large to explore. So the searcher action is discretized by dividing into n directions. In doing so, a set of action is represented as you can see here. A searcher selects an action from a set of the discretized actions. For instance, the searcher that selected action A1 rotates theta A1 and moves a distance of D1. At the end of each episode, positive or negative rewards are given to the searchers depending on the surveillance result, success or failure. If the negative rewards are equally given to the searchers in case of failure, even the approaching searcher is evaluated as ineffective for surveillance, as well as the leaving searcher from the UFB. In this case, therefore, the negative rewards, depending on the final distance to the UFB, are given to the searchers. From this equation, if any of the searchers detect the UFB, the positive rewards are equally given to all the searchers. On the other hand, the negative rewards increases as the final distance d fin to the UFB increases in case of failure. In order for a searcher in state ST to take action AT, the action weight WST-AT is used as an indicator. As the action weight is increased through reinforcement learning, the searcher tends to select this action AT in this state. The action weight in each state is calculated from reverse. After each episode, action weights corresponding to a series of actions are calculated. For this purpose, we present profit sharing with expected value, abbreviated as PS with EV. In addition to the given reward, the action weight is calculated in consideration of the expected value of the reward in each state. After that, the action weight is updated as follows, where EST is the expected value of the reward in state ST, calculated as follows. During each episode, a series of actions in the states is stored. After the episode, The action weight is updated according to the difference between the given reward and expected reward. So the action weight is increased if the reward is higher than the expected one, and vice versa, through the profit sharing with expected value. Okay, because the search state is defined by continuous values, it is impossible to explore the whole state space and calculate the action weights for all the state action pairs. In this presentation, therefore, a relationship between the state and action weights is formulated. For state action mapping, a radial basic function network, which is RBF net, is used. This RBF net is based on a deep neural network composed of 3 input, hidden, and output layers. And radial basic functions are applied to the units in the hidden layer. As a result, the relationship between the input state S and output action weight W is represented by this equation. Connection weights between case unit in the hidden layer and output units are defined for the discretized and output actions. The radial basic function used in the hidden layer is based on this Gaussian kernel. Through state action mapping, the RBF net accepts not only observed states, but also the other similar states, even if the states are not observed by the searchers before the learning phase. For these input states, the action weights of W1A to W1N are derived from the N output unit. This figure illustrates an example structure of this RBF net with 3 searchers. The input state S is first off normalized, and these values are then fed as the inputs to the RBF net and calculated in the Gaussian units. After that, through the connection weights, the action weights from WA1 to WAN are calculated and derived as the outputs. After each episode, action weights are updated by this equation. In this layer, let us note that for the outputs of WA1 to WAN derived from the RBF net, only the output unit corresponding to the action taken in that state is used. In other words, the connection weights of the output units are updated so that output action weight is equal to the output 1 as follows, where delta is an update value calculated from this equation. In a state, the searcher probabilistically selects an action depending on the action weights. For this purpose, Boltzmann action selection is used. The searchers repeat the decision making until the end of the episode. For Boltzmann action selection, each action weight is converted to this following probability, where T is the temperature, which is a time varying parameter. This probability increases as the action weight is increased. So an action with higher weight tends to be selected. Thus, the Boltzmann action selection through state action mapping is a kind of the surveillance policy for the searchers. In the initial learning phase, action weights are uniformly given to all the states for all the actions. In this phase, the surveillance policy allows the searcher to select each action with equal probability. In other words, the searchers gradually learn effective actions from the random actions by detecting their target UFB. However, the searchers based on the random actions seldom detect sophisticated UFBs. And as long as the searchers fail to detect the UFB, the negative rewards continue to be given to the searchers. As a result, the searchers cannot acquire the effective actions to approach the UFB through reinforcement learning. This learning problem is due to the large state space. Therefore, we further apply transfer learning to this problem. In transfer learning, the final action weights in a smaller environment are used as initial action weights in a larger environment. And the state space is represented as follows here. Yes, here. Okay, this figure illustrates the process of transfer learning. In environment D1, the state space S1 is limited around the UFB. In this state space, the searchers are already close to the UFB and arranged so as to surround the UFB. So even the searchers based on random actions can detect the UFB. Moreover, the searchers are allowed to observe the state space and update the action weights sufficiently. After that, the action weights in the environment are transferred to the expanded environment and used as the initial action weights, as you can see here. The searchers mainly observe the additional state space just around here, and update the action weights. This process is repeated until the size of the environment reaches the surveillance area, which is DM. Through transfer learning, random actions of the searchers in the initial learning phase are confined to limited state space and additional state space. In the initial limited state space, the searchers detect the UFB with random actions. So more positive rewards are given to the searchers. And as a result, the learning efficiency is increased and the searchers in the surveillance area are allowed to learn the effective actions to approach the UFB with episodes. In this simulation experiment, single sentinel and 3 searchers are used for surveillance. Each episode, a target UFB comes into the surveillance area. The initial positions of 3 searchers are as indicated in this figure. As for the target UFB, both the incoming position and the destination are randomly selected from the edge of the surveillance area. In the right figure, the sensing ranges of the sentinel and the searchers are provided. The radius of the surveillance area is 300 kilometers. And within the radius of 50 kilometers, the searchers are able to detect the UFB. The searchers moved at the velocity of 300, and the UFB moves at the velocity of 450. As for the searchers, by dividing into 5 directions, the action is discretized, as you can see in each step, corresponding to 0.1 hour. As for the UFB, the moving direction is determined by this resultant force. So the attractive force and repulsive force affected on the UFB are generated from the destination and other searchers as follows. Under the following 3 conditions, the searchers acquire the effective actions to approach the UFB depending on the combination of the input states and the presence or absence of transfer learning. In the condition 1, the searcher state is defined by ds, theta s, and phi s in consideration of only the target UFB. And in the condition 2, the searcher state is defined by ds2, theta s2, ds3, theta s3 for other searchers in addition to the target UFB. And these normalized parameters are fed as inputs to the RVF net. And for these input states, action weights are derived from the RVF net. In the condition 3, the searchers first operate in a smaller surveillance area with a radius of 200 kilometers for transfer learning. After 1,000 episodes, the action weights are transferred to the original surveillance area. Surveillance actions acquired by the searchers through reinforcement learning are evaluated on the basis of the success rate in each 1,000 episodes. This figure shows the results under the three conditions. The success rate of the surveillance under the condition 1 was not increased with episodes. So the final success rate remained at around 5%. On the other hand, the success rate of surveillance under the condition 2 increased to about 22%. So here let us compare the surveillance actions of the searchers under the conditions 1 and 2. In these two movies, while the searchers in the left failed to detect the UFB, the other ones in the right succeeded in detecting the UFB. These figures show the approaching trajectories of the searchers for the same target UFB. In the left, the searchers directly approached the UFB independently from each other. As a result of the actions, the searchers failed in detecting the UFB. In the right, on the other hand, the searchers cooperatively approached so as to surround the UFB. As a result of the cooperative actions, the searchers succeeded in detecting the UFB. These results show that the searchers learned the cooperative actions which are effective for surveillance based on the state defined by the target UFB and other searchers. Okay, while the final success rate under the condition 2 was about 22%, the initial rate for the first 1,000 episode was about 1.5%. This result was as low as the initial success rate under the condition 1. In contrast, the initial success rate under the condition 3 was increased to about 8%. This result shows that the searchers efficiently learn the effective actions. Because of the increased learning efficiency, the final success rate was also increased to about 32%. Compared to the result of the condition 2, the surveillance performance was increased about 10%. Okay, in this presentation, we proposed an area surveillance system composed of a single sentinel and multiple searchers. For sophisticated UFBs, the searchers successfully acquired effective actions through reinforcement learning. In the surveillance simulations, the searchers approached the target UFB in cooperation with each other. As a result, the success rate of surveillance was increased to 22% from 5%. Furthermore, transfer learning increased the initial success rate from 1% to 8.2%. Because of the increased learning efficiency, the final success rate was increased to 32.2%. And this system yielded the best surveillance performance. Okay, from the results, the effectiveness of the cooperative actions by the multiple searchers for the UFBs in this area surveillance system was finally shown. Okay, that's it. Thank you for your kind attention. And if you have any questions and comments, please send me a mail to this address.